Estimating functions. Using methods of differentiation, we may show, for example, that cosine of x is always bounded from the above by 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, and from below by 1 minus x squared over 2 factorial. 2 factorial here is a product of all the numbers up to 2, that is just 1 times 2, which is 2. 4 factorial is the product of all the numbers up to 4. It is 1 times 2 times 3 times 4, and that is 24. This kind of estimates are very useful when dealing with complicated functions. These estimates are based on the mean value theorem. The mean value theorem implies that if f is differentiable on an open interval, and if f prime of x is positive for all x except for a finite number of points, then the function f is strictly increasing. This is a corollary of the mean value theorem. Here it is important that the function to be considered is defined on a single interval. For example, the function tangent of x is defined whenever x is different from pi over 2 plus any multiple of pi, and the derivative of tangent is 1 over cosine squared. This derivative is always positive. So the derivative of the function tangent of x is positive for all x in the domain of definition of the function f, but the function f is not increasing in its domain of definition, and this is possible since f is not defined on a single interval. So what happens here is that tangent is defined on a union of infinitely many intervals, and each component of the graph of the function is increasing itself, but as a whole, the graph of the function tangent of x is not increasing. As an example of the use of calculus methods, we now show that sine of x is less than x for x positive. That is, we show that the blue line, y equals x, lies above the graph of the sine function, the red curve, for x positive. Recall first that angles are measured in radians. The size of an angle in radians is the length of this green circular arc enclosed by this angle, and the green circular arc is an arc on a circle of radius 1 with center at the vertex of the angle. That's how angles are measured in radians, and cosine of x and sine of x are the x and y coordinates of the intersection point of the red ending side of the angle and the unit circle. That is the point indicated by the blue dot. So sine of x is the distance of the blue dot from the x-axis. The green circular arc joins the blue dot to the x-axis but does not go straight. This means that the inequality sine of x is less than x for x positive is a direct consequence of the definition of the sine function, and we would not need any further proof for that. But as an illustration of the methods of calculus, we prove it here by the mean value theorem. So our task is to show that sine of x is less than x for x positive. To that end, we form the function f of x equals x minus sine of x. In order to show that sine of x is less than x for x positive, we have to show that x minus sine of x is positive when x is positive. To do that, we differentiate this function f. Its derivative is 1 minus cosine of x, and this number is positive whenever x is not a multiple of 2 pi. This means that on any interval, the derivative of f of x is positive except for a finite number of points. That is on any finite interval. And this means that the function f of x is increasing on any finite interval, therefore it's strictly increasing, and this means that f of x is larger than f at 0 for x positive. But f at 0 is 0, so this means that x minus sine of x is positive for x positive, and this is what we were supposed to prove. In this example, our task is to prove that cosine of x is always at most 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. I remind you that 2 factorial is the product of all the numbers up to 2, that is just 1 times 2, which is 2, and 4 factorial is product of all the numbers up to 4, which is 1 times 2 times 3 times 4, and that results to 24. In order to prove this, we first observe that the functions in the inequality are even. This means that they take the same value for x than what they take for negative of x. And this means that it suffices to show that this inequality holds for positive values of x. If it does hold for positive values of x, it also holds for negative values of x, because both sides of the inequality take the same value for x than what they take for negative of x. In order to prove this inequality, first for positive values of x, we consider the function f of x, which is the right hand side minus the left hand side of this inequality. That is, f of x equals 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus cosine of x. And our task was to show that the inequality cosine of x is at most 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial is true, and this is equivalent to saying that f of x is greater than or equal to 0. So we prove that f of x is greater than or equal to 0. F of x was 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus cosine of x. Its derivative is minus 2 times x over 2 factorial plus 4 times x cubed over 4 factorial plus sine of x. This simplifies to minus x plus x cubed over 3 factorial plus sine of x. Namely, 4 divided by 4 factorial is just 1 divided by 3 factorial. This is still somewhat complex. We don't clearly see how this derivative behaves. So let us compute the second derivative. It is derivative of minus x plus x cubed over 3 factorial plus sine of x. The second derivative is minus 1 plus x squared over 2 factorial plus cosine of x. It is still necessary to compute the third derivative. It is just x minus sine of x. This third derivative, x minus sine of x, is positive for x positive. This we already know, because we have seen in previous example that sine of x is less than x for x positive, a fact that also follows immediately from the definition of the sine function. So the third derivative of the function f is positive for x positive. This means that the second derivative is increasing for x positive. Now the second derivative was minus 1 plus x squared over 2 factorial plus cosine of x. This means that this second derivative is larger than its value at 0 when x is positive. The value of the second derivative at 0 is simply minus 1 plus 0 plus 1, which is 0. So we conclude that the second derivative of the function f is positive for x positive, and this means that the first derivative is increasing for x positive. So the first derivative was minus x plus x cubed over 3 factorial plus sine of x. This takes a value 0 at 0. If you plug in x equals 0, then every term is 0. So you conclude that the first derivative is positive for x positive, and this means that the function f itself is increasing for x positive. So now we know that the function f is increasing for x positive. This means that the function f, which was 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus cosine of x, takes values which are larger than the value of the function at 0 for x positive. But the value of the function at 0, f at 0, is 0. So we conclude that f of x is positive for x positive, and this means that cosine of x is at most 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial for x greater than or equal to 0. We have strict inequality here when x is strictly larger than 0. We have equality when x is 0. Since cosine of negative of x is cosine of x, as already observed in the beginning of this proof, and since 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial is of course the same as 1 minus negative of x squared over 2 factorial plus negative of x to the fourth over 4 factorial, we observe that this result holds for all x. And this concludes the proof. Using these methods, we can actually show that cosine of x is always between 1 minus x squared over 2 factorial and 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. That is, cosine of x is squeezed between the graphs of these two polynomials, the red polynomial of degree 4 and the blue polynomial of degree 2. This is handy when we have to study the behavior of the function cosine of x near the origin. The main result on which all these proofs are based is the consequence of the mean value theorem, which says that if f is differentiable on an open interval, on a single open interval, and if f prime of x is positive for all x except for a finite number of points, then f is strictly increasing.